Welcome to the lecture on spherical aberration. We have already learned about aberrations. Aberrations are nothing but defects in images. This spherical aberration belongs to the category of monochromatic aberration. Now I will discuss about spherical aberration. This spherical aberration is mainly due to the rays which are incidenting on the lens of different zones. This is in this figure we can observe that these rays, this is the convex lens, this is the principal axis. These two rays are very close to the principal axis and these are parallel to the principal axis. These two rays are known as paraaxial rays. That means the rays which are very close to the principal axis are known as paraaxial rays. When these paraaxial rays, when they incident on the convex lens, after refraction they meet the principal axis at one point called paraaxial focus. Then the image is formed at this point. This paraaxial focus is represented by capital FP. These two rays in this figure, these two rays are away from the principal axis. These are called marginal rays. These two rays are called marginal rays. Marginal rays are nothing but these are the rays which are incidenting on the lens away from the principal axis. These rays after refraction through the lens meet the principal axis at one point called FM. This is known as marginal focus. We know that the distance between the focus and the center of the lens is known as focal length. It is denoted by small f. Therefore, the distance between marginal focus and the center of the lens is known as marginal focal length, small fm. And the distance between paraaxial focus and the center of the lens is known as paraaxial focal length, fp. These paraaxial rays, after refraction through the lens, they meet the principal axis and form the image away from the axis. In case of marginal rays, the image is formed nearer to the lens. That means marginal rays have greater deviation than paraaxial rays after refraction through the lens. The deviation of marginal rays is greater than the paraaxial rays. Therefore, the distances f1 and fp are known as marginal focal length and paraaxial focal length. In the above figure, the rays which are in between marginal rays and paraaxial rays, which are not present in the figure, they form images in between fm and fp on the axis. In this way, for a point object on the principal axis, there are number of images are observed on the principal axis. This defect, then the image is not clear. This defect in lenses, due to which focal length changes from zone to zone, is called longitudinal spherical aberration. The distance from paraaxial focus to marginal focus is the measure of longitudinal or axial spherical aberration. This is also called as axial spherical aberration because this defect is along the axis. Therefore, this is known as axial spherical aberration. The next one is transverse or lateral spherical aberration. These are the marginal rays and these are the paraaxial rays. Then these are marginal rays and these two. If a screen is placed perpendicular to the principal axis and if it is moved in between marginal focus and paraaxial focus, there are different circular images of different sizes are observed. But for a single object, we have to observe a single image. But due to this defect, instead of a single dotted image, point image, then number of circles of different sizes are observed. But in this, at one position where the marginal and paraaxial rays cross each other, a circle of circle of least area is observed. That is the nearest image to the point object. Therefore, this is known as circle of least confusion. The minimum area of circle is observed. This is known as, this is the circle of least confusion in this figure. The radius of circle of least confusion measures the transverse or lateral spherical aberration. That means it is observed perpendicular to the principal axis. Next, if a convex lens is used, this defect is on the right side of the lens, therefore it is taken as positive. If you use a concave lens, then these images are formed on the left side of the lens, that is on the object side, therefore spherical aberration is taken as a negative. Next, how this next concept is how this defect is eliminated. Spherical aberration is minimized or eliminated in different methods. The first method is by using stops. If we observe the above figure, we can observe that there are rays which are incidenting on the lens at different zones. If we allow only one type of rays, then this defect is eliminated. Therefore, in order to eliminate this defect, stops are placed on both sides of the principal axis. Then only one type of rays, either paraxial rays are allowed or marginal rays are allowed. Then a single image is observed. But this method is not suitable because only one type of rays, that means some rays are allowed, but we do not allow all the rays which are incidenting on the lens. Then automatically the intensity of the image decreases. Therefore, stops method is not suitable method, but it is only for some purposes in laboratories, etc. But the intensity of image is very small and the diminished image is observed. Next, another method is crossed lenses. Crossed lens means, if lens is nothing but if a bioconvex lens, it has two surfaces. Two surfaces may have different radii of curvatures or equal radius of curvature. A crossed lens is one. If a lens is made up of material of refractive index 1.5, if the radii of curvatures, that means R1 by R2 are in the ratio of 1:6, then the spherical aberration is eliminated. The lens surfaces must be curved in opposite direction. More convex side should face the more parallel beam. That means incident rays and refracted rays. In these two rays, which ray is parallel, then the convex side should face that side. These are about crossed lenses. Therefore, crossed lens is one, a lens having refractive index 1.5 and radii of curvatures 1:6. And there are some other combinations, mu of 1.6 and then radii of curvature ratio is different. This is the one condition. By using these crossed lenses, we can eliminate spherical aberration. Next, the next important method is by using plano-convex lenses. We know that convex lens means, convex lens means a double convex lens. That means both sides are convex. In this case, we use plano-convex lenses. Plano-convex lens means a lens having one of the surfaces convex and other surface plane. It is known as a plano-convex lens. A lens having one of the surfaces a plane surfaces and the second one is the convex surface, it is known as a plano-convex lens. By using these lenses also we can eliminate spherical aberration. In this case, there are two sides. One is plane surface and the second one is a curved surface. In case of plano-convex lens, in order to eliminate the spherical aberration, the planes, if the rays are incidenting on the convex surface, then This is the spherical aberration. If plane surface is facing the incident rays, then the distance between FM and FP increases. Therefore, in this case, distance between FM and FP is small. Therefore, in case of plano-convex lenses, convex side should face the parallel beam. Then only the longitudinal spherical aberration is minimized. If the plane surface is towards the incident rays, parallel rays, then the defect increases. Therefore, in order to decrease the spherical aberration, we have to use the plano-convex lens facing the convex side towards the incident parallel rays. The next, by using convex and concave lens combination, we have already said that spherical aberration for a convex lens is positive and the spherical aberration for a concave lens is negative, considered as negative. By using suitable combination of convex and concave lenses, spherical aberration is made minimum. Next, the next method is by using two plano-convex lenses separated by a distance. In order to eliminate spherical aberration in telescopes, in eyepieces, etc., two plano-convex lenses separated by some distance are used. In this case, two lenses are taken. For example, if you consider two lenses of focal lengths f1 and f2, and the distance between them is, and they are separated by distance x. These are two lenses, L1 is the first lens and L2 is the second lens, and x is the distance between them. If AB is the light, parallel light incidenting on first lens L1 at the point B, after refraction, it meets the principal axis at F1. It meets the principal axis at F1 in the absence of second lens. Again, this is the incident ray. In the absence of the lens, this is the direction of the ray, dotted line. Due to the presence of lens, after refraction, it meets the principal axis at one point called focus F1 in the absence of second lens. Therefore, L1 F1 is the focal length of the first lens L1. L1 F1 is the focal length of the first lens. Then this is the deviation produced by the first lens. This is the incident ray direction. This is the deviated ray direction. Therefore, this is the angle of deviation for the first lens. Next, when this refracted ray enters into the second lens, it again undergoes refraction. That means it again suffers another deviation. In the absence of the second lens, this is the direction of the refracted ray from the first lens. Then this is known as angle of deviation produced by the second lens. Next, this is the direction of original ray. This is the direction of final ray after suffering two refractions. Therefore, total deviation is delta. Total deviation is delta. In this case, delta 1 is the deviation produced by the first lens and delta 2 is deviation produced by the second lens. In the mathematical expression for removal of spherical aberration is minimum when deviations produced by the two lenses are equal. Therefore, delta 1 must be equal to delta 2. In this triangle BL1 F1, this is delta 2. This is delta 2, and we know that deviation produced by the lens is equal to height of the ray from the principal axis h1 by focal length h1 by f1. This is the deviation produced by the lens. Therefore, deviation produced by the first lens is h1 by the focal length of this lens f1, and the second ray touches the refracted ray from the first lens touches the second lens at height h2. Therefore, deviation produced by the second lens delta 2 is equal to h2 by focal length of this lens. Therefore, H1 by H2 is equal to F1 by F2. This is the equation number 1. Next, we have to derive the condition for no spherical aberration. Therefore, if we observe the figure, there are two triangles which are similar. First triangle is BL1 F1. BL1 F1. This is the height BL1. This is the base for this lens. If we observe the second lens, second triangle CL2 F1, height is H2, that is CL2, and base is L2 F1. Base is L2 F1. These two are similar triangles. Similar triangles means if two triangles are said to be similar, all the angles are equal. In this case, this is a perpendicular 90 degrees. In this case also, if we draw a perpendicular, it is also 90 degrees. This angle is common for both the triangles. The first triangle is BL1 F1. The second triangle is CL2 F1. F1 is common in both the triangles. And these two are 90 degrees. This angle is also, if we draw a perpendicular, this is a 90 and this is also equal to 90. If two angles in the two triangles are equal, automatically the third angle is the same. Therefore, these two triangles BL1 F1 and CL2 F2 are similar triangles. The another property of the similar triangle is the ratios of corresponding sides are also equal. That means this is the height BL1 is the height in the first triangle. CL2, the corresponding side in the second triangle is CL2. This is the height in second triangle, base. In this case, the base is L1 F1. In this case, the base is L2 F1. The property of the similar triangles are, the first one is angles of the three angles in the two triangles are the same, then it is said to be they are said to be similar triangles. And the second property is the ratios of corresponding sides, this height by that height, and H1 by F1, H1 by H2. H1 is BL1, H2 is CL2. And the second set of sides are bases. L1 F1 is the base in the first triangle and L2 F1 is the base in the second triangle. Therefore, H1 by H2, BL1 by CL1 is equal to, this is one pair and the second pair is bases L1 F1 and L2 F1. Therefore, L2 F1 is equal to, if we take L1 F1, if you take, we know that the value of L1 F1, we don't know the value of L2 F1. Therefore, in order to simplify the equation L2 F1, we take L1 F1 total length minus L1 L2, then we get L2 F1. Therefore, this is equal to L1 F1 minus L1 L2. From equations 1 and 2, from equations, this is known as equation 2. From 1 and 2, we observe the left hand sides are equal, H1 by H2, H1 by H2. Then automatically right hand side values are also equal. Then we get F1 by F2 is equal to F1 by F1 minus X. Numerators are equal. Therefore, F2 is equal to F1 minus X or X is equal to F1 minus F2. This is the condition for minimum spherical aberration or no spherical aberration. That means if X is the distance between the two lenses and F1, F2 are the focal lengths of the two lenses, then the condition for no spherical aberration is the distance between the two lenses must be equal to difference of their focal length. This is another method of elimination of spherical aberration. In this way, these are the different methods for elimination of spherical aberration. Next, we conclude that the spherical aberration means if a point object is situated on the principal axis, when monochromatic light is used, then the image formed by this point object is not a single image. Then different sized images are formed on the principal axis. Then the image is blurred. This inability of the lens is known as to form a point image for a point object on the principal axis is known as spherical aberration. This is due to greater deviation of marginal rays. If the deviations of all the rays are the same, then single image is formed, that is all the rays meet the principal axis at the one point. But different images are formed due to different deviations of the rays which are incidenting on the different zones of the lens. Or this method can be eliminated by using crosser lenses, stops, plano-convex lenses, suitable combination of concave and convex lenses, etc. And we can also eliminate this spherical aberration by using two plano-convex lenses of focal lengths f1 and f2 separated by distance x. But the condition between the distance between the two lenses for the elimination of spherical aberration is the distance between the two lenses must be equal to the difference between the focal lengths of the two lenses. These are the different methods for the elimination of spherical aberration. Thank you.